In this video, we're going to finish up section 4.2 with a few more exercises applying some of the things we learned about cyclic groups and cyclic subgroups. So first, we want to find the order of every element in Z18. So remember, and this is kind of the main theorem that we use through a lot of these, the order of an element is the order of the group divided by the GCD of whatever power you have to take the generator to get that element and n itself. So this number is just another, I'm dividing n by one of its factors, so that gives you another factor. So this is just another divisor of n. So I can think about all the different divisors as possible orders. So let's first we'll look at the possible GCDs, and then we'll see how that relates to the orders. So you could have a GCD of 1. Well, that just means they're relatively prime. So in this case, you get 1, 5, 7, 11, 13, and 17 are all the numbers that are relatively prime to 18. And these all have order 18, because they all would generate the whole group. You can have a GCD of 2. You can have a GCD of pretty much any factor of n. And the ones that have GCD 2 are 2, 4, 8, 10, 14, and 16. And if you divide by that GCD of 2, so you get n is 18 in all of these, 18 divided by 2. So these all have order 9. And so we just continue in this way. The next possible GCD that you could have with 18 is 3. And those numbers are just 3 and 15. And they both have order 18 over 3, so that would be 6. Next, you could have a GCD of, well, you can have a GCD of 4. 4 doesn't divide, or 5, but you can have a GCD of 6. And that happens with both 6 and 12. And so both of those would have order 18 divided by 6, so order 3. Next, you could have a GCD of 9. That only happens with 9. And so that has order 2. And finally, you could have a GCD of 18. Or 0, I guess. But 18 makes a bit more sense here. So the idea is, you take it to the 18th power, you get back to 0. So, or power in this case would be adding 18 times. So 0 is the only one you get for that. And so that, of course, has order 1. In the next example, we look at the number of generators is supposed to be a 1 here, that a group can have. So first we find cyclic group with exactly 1 generator. So with 1 generator, well, there's a couple examples that come to mind. You could do Z1, that's just the element with just 0 in it. Under addition, of course, that generates itself. But you could also have Z2 as 1 generator. That has just 0 and 1. But 1 generates the group. 0 does not. So it has exactly 1 generator. And you could also take the group of units for 2. So numbers that are relatively prime to 2 are just 1. So there's only 1 element in there. But under multiplication, so 1 generates itself. What about 2 generators? Again, exactly 2 generators. One easy example there would be Z3. So both 1 and 2 would generate the group, but 0 would not. And then next is 4 generators. So at this point, we're starting to, as we get to bigger numbers, we're thinking, well, if you remember our example before, we're just looking for, the generators are the ones that are relatively prime to whatever that subscript is. So we want the number of relatively prime numbers to be 4. And an example there would be Z12. It has 1, 5, 7, and 11 would all be relatively prime, and so they're all generators. And everything else would not be a generator. So it has exactly 4. And then for the question, how about n generators? So we notice we skip 3. And in fact, if you want exactly n, that means n must be even. And I don't really talk too much about, having that many generators. We're basically asking how many elements are relatively prime to a given number, and can that be any number that we want? And it turns out no. It has to be an even number, and not every even number works. So for example, 14 can't have one with exactly 14 generators. If you want to look this up, if you're curious, you can look at Euler's totient function is really what we're doing here. We're asking, we want the totient of the order of the group to be equal to n, and we want a group of some sort, or order of a cyclic group to, so this has to be Z, let's say M, to have that many relatively prime numbers, and it just doesn't work for every number, and it only works for even numbers, and it doesn't even work for every even numbers. So you could look at what are called non-totient functions, or sorry, non-totient numbers are the numbers that wouldn't work in this case. Next, we have two distinct primes, and we want to know how many generators Z PQ have. So again, we're asking how many numbers are relatively prime to the product PQ. So you can imagine most numbers, like a P and Q, are fairly large primes. Most of the numbers are relatively prime to that product. And, well, remember this contains 0, the identity, and then up to PQ minus 1. So it has PQ elements in it, but 0 is not included. So there are, so out of the PQ minus 1 non-zero elements, again, most of them are relatively prime. Which ones are not? Well, the ones that are multiples of P and the ones that are multiples of Q. And how many of each do you have? There would be, there are Q multiples of P and P multiples of Q. So we have to take those out. So out of the PQ minus 1 non-zero ones, we have to subtract P that are multiples of Q and the Q that multiples of P. And I know you might be thinking, what if they happen at the same time? Well, we kind of already included that with taking the 0 out. 0 is a multiple of both. But multiples of both would have to be PQ or higher, and that's not part of this. So we don't have to worry about ones that are multiples of both. And this, if you do some algebra, this factors into P minus 1, Q minus 1, which gives us an idea of how this would generalize if you looked at P or Z PQR, so 3 distinct primes. Then the number of generators would be P minus 1, Q minus 1, R minus 1. And that would continue as long as you keep doing distinct primes. And it's also showing us, the totient function of PQ for distinct primes is P minus 1, Q minus 1, and same totient function of PQR. So again, generators, we're just looking for the totient function, number of relatively prime numbers less than that number. In these next three problems, we want to show that two things have the same order. And so we need a strategy for doing that, because remember, the order is the smallest value, the smallest exponent that would give you the identity. So I'll put up at the top here a strategy that we're going to use. And that is, if we can show, like if we have x and y in the group, just to make it different from what we have here, if x to the n being the identity implies y to the n is the identity, and vice versa, so if and only if, then they have the same order. We can think of this as a little lemma. And if you want, you can prove this lemma. So I'll put this as a lemma. So prove that if this if and only if statement is true, then they have the same order. But that's what we're going to do. We'll show that if one has order n, then the other has to have order n, and vice versa. So here we want to show A has the same order as its inverse. So let's do both sides of this. So there's two components to this. So if A to the n is the identity, well, you could multiply both sides repeatedly by A inverse to eventually knock that side down to the identity. So you'd have the identity on the left-hand side, and then n copies of A inverse on this side. But that's clear. And then you can repeat that, right? So if I suppose that A inverse to the n gives me the identity, I can now repeatedly multiply both sides by A, and then I'd have the identity on the left, and then n copies of A on the right. So we do have both, right? So if A to the n is the identity, if and only if A inverse to the n is the identity. And so by our lemma, they have the same order. So the order of A is equal to the order of A inverse. So you can see how that lemma helps, because we never have to consider anything being the smallest possible. We're just supposing that some power brings us to the identity, and the other one also has that. You can sort of think of it as the set of numbers that bring one to the identity is the same as the set of numbers that bring the other to the identity. So they would have the same smallest number. So a little bit of a hint on how to prove that as a lemma. Okay, next, the order of an element is the same as the order of a conjugate of that element. So when you do this G inverse AG, or you could do it the other way around, G AG inverse, that's what we call a conjugate of that element. So we're trying to prove that an element has the same order as any of its conjugates. So that's true for any G that I pick. So again, going through this same strategy, let's suppose A to the n is the identity. And now let's prove that this has the same, or that if I take this to the nth power, I also get the identity. Well, let's see what happens if I take this to the nth power. And this is this kind of demonstration here, the algebra that's going to happen here is part of the reason why we look at the conjugate in the first place, because this is just n copies of itself. But when you do this, you keep getting G's and G inverses canceling out. So that'll cancel out with the next one. This will cancel out with the one prior. So what you end up with is a G inverse, n copies of A, because all the other G and G inverses have canceled out, so A to the n. And you get G, or this G at the n. Well, A to the n, we're assuming that that's the identity. So this is the identity, so this is G inverse G, and of course that is the identity. So we did show that this conjugate does give you the identity. So we got first half of it done. Now we go the other way around. We suppose G inverse AG, when I take that to the nth power, I get the identity. Well, we just showed, like, this didn't, from here to here, underline these. So going from here to here didn't require any assumption. That's just algebra. That's just a bunch of things canceling out. So this implies that I can just replace this with this. So G inverse A to the n, G, is the identity. And now I just start moving the G's to the other side. So if I multiply on the left by G, I get A to the n G is G. And then multiply on the right by G inverse. So A to the n is G times G inverse, which is E, which is what we wanted to show. So again, therefore, the order of A is the same as the order of G inverse AG, or it's one of its conjugates. Our last one is showing that the order of a product AB is the same as the order of its other product BA. Again, if it's abelian, that's trivial, but if it's not abelian, we still have to prove something here. Here we don't really need to use our lemma. We'll, actually no, yeah, we're still using our lemma, but we'll only do one side of it because it's pretty obvious how you would go the other way. So we suppose AB to the n is the identity. Oh, yeah, I see. We're going to make these all if and only if statements. So I can rewrite this. Remember, AB to the n is just AB, 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 n times. So if I take that first A and pull it out, and then take the last B that will appear, pull that out, then what I have in the middle is BA, 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 a bunch of BAs in a row. How many of them? Well, n minus 1 of them. So you have BA repeated n minus 1 times. And that's still the identity. And now I want to move this A and this B to the other side. So I'll multiply first on the right by B inverse. So I have A and then BA to the n minus 1 is equal to B inverse. And you might be thinking, you know, I'm trying to isolate the BA to the n minus 1, but I'm not. I'm actually going to now multiply by B, but this time on the left. So I'll put here. So I multiplied both sides of this equation by B inverse. But now I'm going to multiply both sides of this equation on the left by B. But notice that still gives me back to the identity. And now I have BA and then n minus 1 copies of BA, so I have BA all the way to the n, and I still get the identity. So I just thought that was kind of a little neat way to do that. So I do have, and this is a chain of if and only ifs, that AB to the n is the identity if and only if BA to the n is the identity, which means, again, the set of possible powers to get the identity is the same, so they have the same smallest. So the order of AB is the same as the order of BA. Okay. Next, we have a group, and we have 2 elements in that group. We want to prove that if the order of A is m and the order of B is n, and those 2 orders are relatively prime, then the intersection of the cyclic subgroups generated by A and B is just the identity. They can't have anything else in common. So this is another thing we end up doing a lot in algebra, showing that the intersection of 2 things is the identity. Strategy for proving that is to assume there's an element in there and then prove that that element is the identity. So I'm going to let x be part of this intersection. Notice I'm letting it be an arbitrary element of the intersection. If I show that that element must be the identity, then that's the only thing in there. Well, being in there, of course, means it's a power of a and a power of b. So x is a to the I, and x is also b to the j for some integers I and j. Now we had a theorem that said what the order of x is within each of these cyclic subgroups. So by theorem 4.13, using it twice, we have the order of x is looking at A, or looking at this as the, x is part of this, so thinking of that as our main group. The size of that group is M, and I divide by the GCD of M with I. Well, we said this before, taking M and dividing it by one of its factors just gives me another factor. So this does imply that the order of x does divide M. And similar for the other one. And the order of x is n over the GCD of n with j. And again, that's just some other factor of n. So this means the order of x does divide n as well. So it is a common divisor of both n and m. But the GCD of m and n is 1, so they're relatively prime. So that forces the order of x to be 1. So we'll put since the GCD of m and n is 1, this implies that the order of x has to be 1. But there's only one element of order 1, and that's the identity. So x is the identity. Our next example, we have an abelian group that contains a pair of cyclic subgroups of order 2, and we want to show that it must also contain a subgroup of order 4. And we ask the question, does that subgroup of order 4 have to be cyclic? So let's show that the existence part first. So let A and B be cyclic subgroups of order 2. Subgroups of order 2. So say A looks like E with little a, and B looks like E with little b. Now these are different subgroups, so we're assuming that A and B are not the same, and we're also assuming that they're size 2, so A and B are also not the identity. So A is not the identity, B is not the identity. So there are three different things. E is the identity, A and B, three distinct objects, or three distinct elements. Now, we had a result earlier that said that when the group is abelian, the product AB is a subgroup. So AB, which would just be all the products, so E with E, E with A, E with B, and A with B. That this is a subgroup. Now you might be thinking immediately, well, that has to be of order 4, doesn't it? But not necessarily. Like if we didn't have these assumptions, then maybe not, because AB could be one of these. So AB could be B, but that would force A to be the identity. AB could be A, that forces B to be the identity. Or AB could be the identity, but that forces A and B to be each other's inverses. But that's not possible because this is also the group generated by A. So A is its own inverse, and B is its own inverse too. So this can't be the identity either. So this is actually 4 elements. So we can say it is a subgroup of order 4. And it was kind of the obvious thing to do if you wanted to create a subgroup of order 4 and you had 2 subgroups of order 2, just multiply them together. Does it have to be cyclic? You might be thinking, no. I mean, there's no real, the group itself wasn't cyclic to begin with. And in fact, if you took Z2 cross Z2 cross Z2, group of order 8 that's not cyclic, has within it Z2 cross Z2 as a subgroup. And it has many cyclic groups of order 2 that could create it, but that is not cyclic. So the answer to this question is no. And last two, first, an important result that's hidden as an exercise here is that the order of an element in a cyclic group must divide the order of a group. Well, we're going to show that in general. It doesn't have to be a cyclic group. But this is also important. And we've kind of already hinted at it quite a lot at this point. So let G be a cyclic group, so say generated by A, and G some element of that group. Then, of course, G is some power of A for some integer. And let's suppose the order of G is n. Suppose we need to put finite here, but that's kind of implied because we're talking about orders. So by our theorem that we've been using a lot here, 4.13, the order of G is the order of A to the K, but that's n divided by GCD of K with n. But we've said many times now, that's some divisor of n. So I'll just put that's a divisor of n. But that's telling me the order of G divides n. And the last thing I want to do is, while the book goes through a method of repeated squares, I want to show you a different method, which is called the square and multiply method. And I'll show with this example, but I think I must have picked these numbers randomly, or maybe it came from the book. But it turned out to be a somewhat trivial example, and so I'll show 2 examples, or a separate base. So let's first talk about the steps in doing this. Also, by the way, I also picked these numbers because, normal calculators wouldn't be able to do this. You're taking this number to this power and then finding its remainder mod 582. So an ordinary calculator wouldn't be able to do that, but if you threw this into Wolfram Alpha, it would do it no problem. So to come up with a kind of more real example, or I guess when I say Wolfram Alpha, I mean that it can actually calculate this. It'll give you the millions of decimals, or the millions of places that it has where a calculator wouldn't do that. But this, is a method that works, no matter how big those exponents are, whereas, a computer might crash if this exponent gets too big. All right. So the first thing to do is write the exponent in binary. So in this case, 3171 in binary is 11000 110011. Step 2 is starting with the base, ignoring the leading 1. It always has a leading 1. Every time you see a 1, you square and multiply. And by multiply with the base. And every time you see a 0, you just square. And each time you reduce, so each time you reduce by the modulus. In our case, the 582. So one way to do this kind of systematically or organizing yourself, I'll write this number, which happens to be a palindrome, but I'm going to write it. You do write it from leading digit down. And then just write what you get at each step. So the first step would be the 292. And then with this first one, I'm going to square it and then multiply by the 292, which in this case ends up being just cubing it. And then you reduce by 582. What ended up being peculiar here is you got 292 again, and then if you squared, you also got 292. So it turns out at every step you just ended up with 292, which means at the end you get 292. So that was, I have to imagine, crazy amount of luck that happened. So I want to do another example with you where numbers are maybe a little bit more interesting. Actually, it might not be luck. If you notice, the 292 is one more than half of this number. So maybe that was the reason why. Actually, is that true? I'm not sure. Yeah, I think it is. Okay, so I want to also try in this column 135 is the new base, but I'll keep the same exponent. That's why I wrote this same order again. And we'll still mod the same number, still mod 582. So you do start with 135, and you square and multiply. So you'll square 135, multiply by 135. So that first step really is cubing it. And so here you actually do get a remainder that's different of 261. The next one is a 0, so you just square the 261. So squaring 261, modding by 582, you get 27. So now we're going to get some different numbers. I'm going to square a couple more times, so squaring the 27 gives me 147 after modding. Squaring again gives me 75. Now we have a couple of 1s, so we square and multiply again. So square and multiply, remember you don't square and multiply by that number, you still, every time you do the multiply, it's with the base. So I square 70, I square the 75 and then multiply by 135. That gives me the 447. Square and multiply again, I get 261. Well, we saw that before, so I know when I square, I get the 27 again. So I get in a little bit of a loop here. So squaring a couple more times, square and multiply. Because of the pattern that ended up happening here with our exponent, we get that. And we do get 261. So this time 135 to the 3,171 is 261 modding by 582. Okay, so that'll be it for this video, and in the next video we'll start into chapter 5 on permutation groups.